Hi everyone, I'm Jisha from Intel Labs. Today I will give a talk on neural dynamics discovery via Gaussian process recurrent neural networks. We intend to explore how to extract low-dimensional, smooth, and time-evolving latent trajectories through high-dimensional time series. Dynamics discovery is always challenging in extracting complex dynamics from high-dimensional noisy neural data. This figure shows the conceptual illustration of this kind of topic. Let's firstly see the center figure. The population activity lies in a plane. Each point represents the population activity at a particular time and can be referred to using its high-dimensional coordinates R1, R2, R3, or low-dimensional coordinates S1, S2. The points trace out a trajectory over time. In the left figure, the population activity R1, R2, R3 can be reconstructed by taking a weighted combination of the latent variables S1, S2, where the weights are specified by the matrix. In the right, the latent variables S1 and S2 can also be obtained by taking a weighted combination of the population activity R1, R2, R3 with another transformation. In general, the points in R1, R2, R3 space will not lie exactly in a plane. The dimensionality reduction technique tries to find latent variables that can reconstruct the population activity as well as possible. The reconstructed activity can be interpreted as the denoised firing rate for each neuron. Let's be more consistent with the notation in our main paper. Our work is exploring an interpretable latent dynamics Z that can reconstruct observations X well. Z is normally laid in a low-dimensional space. The number of dimension is the number of latent variables used for describing the process. And X is always noisy. Their dimension is the number of simultaneously recorded neurons, which is normally hundreds or thousands. The left figure is an example of neural data, which is normally recorded with spikes, which have the timestamps. We can beam through either high or low resolution and finally get count-valued data. The latent dynamics is always very complex and nonlinear. For example, the Lorentz dynamics shown here is highly nonlinear. The evolution of latent trajectory of three-dimensional latent variables are from the blue points to the red point. Some models are proposed to model the latent dynamics Z. The linear dynamic model is the first one. Each current Zt depends on last time step. The model is efficient and always coupled with Gaussian noise, which is very easy to be inferred. However, they fundamentally cannot capture the nonlinearity. The second choice is Gaussian process, which considers a pairwise correlation of time points instead of considering explicit temporal dynamics. Recurrent neural networks is powerful. However, by directly model Zt as a hidden state, it will heavily depend on the initial state estimation, and Zt will finally become deterministic nodes. Our first contribution is modeling the latent dynamics via a stochastic RNN model. The latent variable Z is from a Gaussian, but both its mean and variance function is obtained via two neural networks whose inputs are from the hidden states of the RNN. The two main motivations here are, first, it's still be able to model the complex dynamics, and second, it's better for uncertainty propagation. While the intensive experiments, we found that the proposed dynamic model is able to both capture the complex state transition structures and also model the long short-term temporal dynamics efficiently. Mapping functions reveal how latent states generate noisy free observations. A nonlinear transformation is often ignored when pursuing efficient and tractable algorithms. Some research explored a nonlinear embedding function using deep neural networks. which requires a large number of data to train a large set of model parameters. In this paper, we employ a non-parametric Bayesian method, Gaussian process, to model the nonlinear mapping function from latent space to the observation space, which requires much less training data. Also, it provides two advantages. First, it can propagate uncertainties. Second, it can be used for describing the turning curve of neurons, which is normally smooth, and a Gaussian process with radial basis function is a good choice. Neural responses can be mostly categorized into two types of signals, i.e. continuous voltage data and discrete spikes. We use Gaussian distributions for generating continuous voltage data. For neural spike trends, normally a Poisson observation model is commonly considered to categorize the stochastic noisy process. In summary, we show our Gaussian process recurrent neural networks called GPRNN in the graphic model. Three main contributions are indicated. The proposed GPRNN model models the dynamics of hidden states Zt with an RNN structure and generates latent dynamics Zt given hidden states. Both hidden states Zt and latent states Zt contribute to the future hidden state. The latent states Zt are mapped to the observation Xt via a Gaussian process mapping function. The observations can be either Gaussian response or the Poisson response. The challenge here is how to infer latent function f and z. Because we focus on the latent dynamics z, and thus it's better if we can integrate the latent function f out. For Gaussian response, it's easy to integrate the latent function out due to conjugation, while for the Poisson response, it cannot. Next, we will separately talk about these two situations. For the Gaussian response, we will infer z based on x, which normally have many choices, such as Laplace approximation, moment matching, and importance sampling. Recent work has focused on utilizing variational inference for scalable computation, which takes advantage of both stochastic and distributed optimization. Additionally, inference networks improve computational efficiency while still keeping rich approximated posterior distribution. Thus, we apply variational inference with different kinds of powerful inference networks. We consider the approximated posterior as a Gaussian whose mean and variance are the outputs of a highly nonlinear function of observation x. Here we consider 5 structured Q distributions by encoding x in different sequential patterns shown in the table. The first one is the vanilla mean field method. The second is variational O2 encoder. The third is LSTM conditioned on future observations. The fourth is LSTM conditioned on past observations. And finally, we use the strong bidirectional LSTM conditioned on both past and future observations in the work. The mean and variance of the latent states Zt is obtained via either or both two LSTM hidden states mapping. Let's move to the Poisson response case, in which case the latent function f cannot be integrated out. In general, we adopt composing inference, fixing latent function f or latent dynamics z, while optimizing the other in a coordinate-ascending manner. First, let's consider how to optimize the latent function. We utilize Laplace approximation techniques. The mean and the precision matrix can be computed using the Bayesian rule. Furthermore, the mean f hat can be obtained by optimizing the function psi. The next problem is that how we can further integrate the latent function out based on psi. A Taylor expansion of the psi fi around the hat fi is used, and thus an approximation px condition on z to the marginal likelihood can be obtained in a closed form. It finally goes to the problem as we discussed before. That is, we can integrate out f and obtain the marginal likelihood of px condition on z. Now we can use any approximate inference techniques infer latent states. We adapt composing inference, fixing latent function f or latent dynamics z, while optimizing the other, until the convergence. Here is the simulation results, root mean square error of latent trajectories reconstructed from various simulated models. We compare two latent dynamic models. The first one is the first order autoregressive, we call AR1 GPLBM, and our model called GP-RNN. Three mapping functions are used for simulation: linear, tangent, and sine. And 5 variational approximations listed in the table are used for do the inference. The observations are either Gaussian response or the Poisson response with 50-dimensional observation neurons and 200 time points. The underlined and broad fonts indicate best performance. While LSTM provided the best inference results compared to other 4 methods. And also, GP-RNN consistently outperforms the AR1 GPLBM, which means the RNN latent dynamics is useful for reconstructing the complex dynamics, such as the Lorentz dynamics. The further details result with standard errors can be found in the supplementary material. This table shows the mapping function analysis. We compare GP mapping and neural network mapping. The mapping functions are shown with either linear, tangent, and sine functions. Both of them are combined with an RNN dynamical model component. We simulate 50 trials and present average root mean square errors results across all trials. N indicates the number of data points for training in each trial, and the result is a subsequent 50 time points for testing. As shown in the table, smaller datasets may affect latent dynamics recovery, but a Gaussian process mapping enhances nonlinear embedding recovery. While if we have more data, both GP and the neural network performance similar. Related models are listed in the above table in the same research line that is used for recovering latent dynamics from neural data. We point each model components and highlight our stochastic RNN dynamic and Gaussian process mapping function. LP and VI means Laplace approximation and variational inference techniques. The table below shows the R-square value of our method and other state-of-the-art method for the prediction of Lorentz-based spike trains, which means we generate the spike trains using a Lorentz dynamics. GP-RNN fitting results are the best with respect to each dimension of latent trajectory, with highest R-square value. We also apply GP-RNN in real dataset containing the neural activity from visual cortex that is open to grating stimulus. True firing rates for 2 example neurons are shown. In the figure A, there exists a clear pattern in the firing rate time series given the grating stimulus. In the figure B, 2-dimensional latent trajectories of 10 out of 30 trials using PFLDS, PGPLBM, and GP-RNN are shown. The color denotes the phase of grating stimulus. Each circle corresponds to a period of latent dynamics who has 90 time points. Each trial is estimated from 63 neural spike trains. The latent embedding is smoother and more structured when applying GP-RNN, which is interpretable since the stimulus is sinusoid for each orientation across time. We can tell that the phase of latent dynamics inferred by GP-RNN is base locked to the phase of the stimulus. Please find more details in the attached link, and if you have any problem, please contact us. Many thanks for your listening.